Hello students, today we'll complete part 3 of extraction of metals and metallurgy unit 6 class 12 science chemistry. This is the flow chart where the steps involved in extracting of metal from their ores are being shown. So once we get the ore from the earth crust, we have to crush and grind it to remove the gangue. Then we follow the concentration of the ore where different steps involved that already we have seen: gravity separation method, magnetic separation method, flotation and leaching method. Next step is roasting and calcination. That means the concentrated ore is being converted into their oxide by this roasting or calcination process. Next we do reduction. After doing the reduction of the metal oxide ore to the metal, we follow the refining of the metal and then we get the pure metal. So up to concentration already you have studied. Today we'll complete the roasting and calcination part and we'll see the principles, the metallurgical principle from thermodynamic that influence the that helps in the reduction process. So basically this part will complete, and the initial topic of this reduction part we'll see in this presentation today. So the steps of metallurgy are concentration of ore, that is already completed. Next, conversion of concentrated ore into their oxide. So this we are going to do today. Next, reduction of metal to metal oxide to metal. Here principle involved we'll see, and next later on we'll do this refining of the metals. Conversion of ore into oxide. Now it is being said that metal oxides are easier to reduce. Okay, you just have to remove the oxygen and you can reduce the metal oxide. This process is much more easier than to reduce the sulfide or carbonate ore. So what we do is, the given ore, if it is sulfide or carbonate, we try to convert them into the oxide form before we proceed further, and this is being done by roasting or calcination method. Now in roasting method, the ore is heated in regular supply of air. Air means what? It is heated in excess of oxygen at a temperature below the melting point of the metal, so as it can convert into the oxide ore. Okay, so you have to remember, in roasting process the ore is heated in excess oxygen and the process is being done, the heating is done below the melting point of the metal, so that you get the metal oxide ore. Generally sulfide ores are converted into the oxide by roasting. So roasting method is useful for the metal sulfide ore. Metal sulfide ore is being converted into metal oxide ore by the roasting process. It is also used to remove the impurities as a volatile oxide. One example is taken, zinc blend ZNS. See, it is a zinc sulfide, okay, sulfide ore of zinc. It is heated in excess of oxygen. You are getting zinc oxide and sulfur dioxide. Sulfur dioxide is the impurity. The sulfur impurity is being removed as sulfur dioxide. It is a gas and hence it is said volatile oxide. So the impurity is being removed as a volatile oxide. So this is your roasting process. In calcination, what happens? Here the ore is heated in limited supply of air or oxygen as to convert the carbonate ore into the oxide. Calcination process is useful for the carbonate ore of the metal. Okay, here also the volatile impurities goes away from the metal oxide ore, and in this process moisture also, if any moisture is there in the process, that also get removed. Example, calcium carbonate is a carbonate ore of calcium. If you heat it, you will be getting calcium oxide, carbon dioxide. Okay, carbon dioxide is also gas, so it leaves the compound in the form of the volatile oxide. The gas removed, so it is a volatile compound. Do remember one thing, in calcination you see, carbonate ore you are treating. In carbonate ore already oxygen is there. So to remember, in calcination process you have to heat the ore in absence of oxygen or in very less supply of air or oxygen. Okay, so these are the two methods of converting metal ore into the oxide, because it is easier to reduce the oxide than to reduce the sulfide and carbonate ore of the metal. Next, reduction of oxide to metal. So once you get the oxide of metal, next step for the purification of ore into metal is the reduction of oxide to metal. In this process of converting metal oxide into metal, the reaction involved is the reduction reaction. It needs a suitable reducing agent. For reduction reaction you need a suitable reducing agent depending upon the reactivity or reducing power of the metal. Okay, the common reducing agent used are carbon or carbon monoxide or any other metal, any other reactive metal, rather aluminum, magnesium, etc. So once you get the metal oxide, next step is to reduce the metal oxide into metal. That means oxygen part from metal oxide you have to remove so that you get the metal. And for this you need a reducing agent. This is some common reducing agent. Now, before we go for the reduction of metal oxide into metal, we must have some knowledge about the thermodynamic principle of metallurgy, because this is going to help us to carry out the process with much lesser cost and efficiently. Now, in the thermodynamic principle of metallurgy, we get the basic concept of thermodynamic that help us in understanding the condition of temperature and selecting the suitable reducing agent in the metallurgical process. So what is the importance of thermodynamic principle in metallurgy, or in the before we go for the reduction process? It helps us to choose the temperature condition and to choose the suitable reducing agent for the process. Okay, now see, from thermodynamic or from class 11 thermodynamic chapter, we know this equation. This is the Gibbs free energy equation. Now, this is the basic thermodynamic equation where delta G, that is Gibbs free energy, is equal to delta H minus T delta S. Okay, delta G is the Gibbs free energy change, delta H is the enthalpy change. That this delta H tell us whether heat will be absorbed or heat will get evolved in the reaction. T is the temperature in Kelvin scale, and delta S is the change in entropy. Entropy means randomness. Okay, and this delta G value tell us whether the reaction is spontaneous or non-spontaneous or at equilibrium. If delta G is equal to 0, then the reaction will be at equilibrium. If the value is negative, then the reaction is feasible or possible, and if delta G value is positive, that means greater than 0, then the reaction is forbidden, is not feasible. Okay, so from here we can say whether a reaction is possible or not. So this is the thermodynamic equation. This equation going to help us. Now let's see how it will help us. Okay, so delta G value tell us whether a reaction is possible or not. If the value is negative, it means the reaction is possible. So that is known to us. Now one example is taken here. We have considered the reduction of iron oxide. So we have chosen a metal oxide, iron oxide. In the reaction it will get converted into iron and it will form half oxygen. Okay, in this process or in this reaction, the delta G value come as positive. Let's say the value is plus 40. Okay, the values are frictional. Okay, these are not real value, just we assume that the value is positive and let's say it is 40. Now if it is 40, if it is plus 40, delta G value is positive, that means what? Is the reaction possible? No, the reaction is not possible. Delta G value, if it is positive, the reaction will not be possible. Okay, now one more reaction we have chosen where carbon or coke react with oxygen and form carbon monoxide. Now in this reaction the delta G value is negative and the value is largely negative, that means the value is higher, okay, negative, but the value is quite higher. Let's say it is high, minus 100. Okay, now first reaction is not possible, second reaction is possible because it have higher negative delta G value. If you combine these two reaction, what you get? You are getting FeO plus carbon forming Fe plus carbon monoxide. So in this reaction you see metal oxide get converted into free metal and carbon act here as a reducing agent. Now let's see whether this reaction is possible or not. Now the net reaction you are getting by combining first two reaction. So delta G value what you'll get, that will be also combination of first two reaction. For this net reaction, delta G net will be the combination of first two reaction. So what are the value? The values are plus 40 minus 100. So if you sum up, you will be getting the value of delta G as minus 60. That means negative. That means if you couple up these two reaction, the net reaction you are getting delta G to be negative. So what happened? First reaction, directly iron oxide you cannot reduce to iron, but if you are taking the help of a reducing agent, then your reaction is become feasible. So that is called the coupling reaction. So thus the delta G value, with this delta G concept you can reduce the metal oxide, okay, by using some reducing agent. By combining the reactants, by combining the reactions, we are getting negative delta G value, hence the reaction become feasible. Now reducing agent carbon, okay, this carbon is the reducing agent here, is helping the extraction of metal here. In this regard, Ellingham diagram, okay, we use a graph that is called Ellingham diagram, help us to choose the reducing agent. We are not choosing only iron, we have many other metal. So which reducing agent will be effective, that can be known by using Ellingham diagram. So what is that Ellingham diagram? It is a graph plotted between delta G versus temperature in Kelvin scale. Now this is your Ellingham diagram. In this Ellingham diagram, see, delta G is plotted in y-axis, in x-axis you are getting temperature from 0 degree to 2000 degree centigrade you are getting, and different reactions are given here. Let's see some facts about your Ellingham diagram. The first point is delta G versus temperature graph plot for various reaction. Ellingham diagram, or it's also known as epigram diagram, it means this is a graph plotted between delta G versus temperature for various reaction. Here you see different reactions are given. This is one reaction, this is one reaction. So for different reaction you are getting this delta G versus temperature plot. It helps us to choose reducing agent. This point is very much important. What is the use of this Ellingham diagram? It helps us to choose the reducing agent for reduction of oxide at a particular temperature. So it helps us to choose the reducing agent, and it also gives the information at what temperature the reaction will be feasible. Next, in this diagram all reactions are oxidation reaction. See here, zinc plus oxygen forming zinc oxide, carbon plus oxygen forming carbon monoxide, magnesium plus oxygen, magnesium oxide. So all the reaction presented here are the oxidation reaction. Each plot is a straight line, okay. See, this plot is straight line, many of the plots are straight line, but in some cases you are getting small deviation, okay. Few curves you get, few plot you are getting where small deviation is there. Now why this deviation occurs? This deviation occurs because of the phase transition. Phase transition means it might happen that the metal was solid and it is going to the liquid state, that, or from liquid it is going to the gaseous state, or from gaseous it is going to the liquid state. For this kind of change, for this phase transition, you are getting this bend. Otherwise most of the lines are straight line, okay. So each plot is straight line. Small deviation in some cases are due to the change in phase, that is liquid to gas or solid to liquid, etc. At a given temperature, the element present at the bottom can reduce the oxide of other element present above it. So it means what? It means that if you have chosen the temperature 800 degree centigrade, okay. So at 800 degree centigrade, what will happen? At 800 degree centigrade, the element present at the bottom, which element is present at the bottom? Magnesium. So magnesium can reduce the element present above it. That means Magnesium can reduce aluminum oxide, it can reduce zinc oxide, it can reduce carbon dioxide, iron oxide, everything. So at a particular temperature, the element that is present at the bottom can reduce the metal oxide or the oxide of other element that is present on the top. And the element that is present at the bottom is highly stable. Why it is highly stable? One thing you see here, for this the value, the delta G value is very negative, minus 1100. So minus 1100 means what? The reaction is, oxidation reaction is feasible, so their oxides are very much stable. So this point is also very important. At a given temperature, the element present at the bottom can reduce the oxide of other element present above it. Lower the curve in the diagram, more stable the oxide form of the element as it possesses more negative delta G value. So in this graph, magnesium oxide will be much stable because their delta G value is the highest negative. So these are some fact about your Ellingham diagram. Let's see the application. So from the graph, okay, from the Ellingham diagram graph, I just took out a portion. So here what is given, here the delta G value versus T I have plotted. Now this broken line, okay, this broken line is for the reaction of carbon, oxidation of carbon, that is carbon plus oxygen to carbon dioxide, and this line, this blue line, is for the oxidation of iron to iron oxide. So the values you see at temperature 0 for the conversion of iron to oxygen forming iron oxide, the value is around minus 450, okay, and at temperature 0 for this conversion carbon plus oxygen to carbon dioxide, the value will be minus 350. Here it will be more than 300 or less than 400, so it will be 350 around. Now see, case 1, at temperature 0 we have chosen the reverse reaction because we have to go for the reduction reaction. So if you are reducing iron oxide, what it will form? It will form iron plus half O2. Delta G value for the reaction, for the opposite reaction, was plus 450. So if you have reversed the reaction, the actual value was minus. So if you reverse the reaction, the value will become plus 450 kilojoule per mole at temperature 0. And for this reaction, carbon plus oxygen forming carbon dioxide, oxidation reaction I have chosen here. What is the value? The value is 350. That means for metal I have reversed the reaction, but not for the non-metal oxidation, okay. So here the delta G value will be as it is, and the value is around 350 kilojoule per mole. If you sum up this two reaction, what you are getting at temperature 0, you are getting delta G value to be plus 100, plus 450 minus 350. If you sum up, the value will be plus 100. If delta G value is positive, the reaction is not feasible, okay. That means if you are using carbon as reducing agent for reduction of iron oxide to iron, and if you are doing the reaction at temperature 0, you will not get the desired result because the reaction won't be feasible as delta G value is positive. Now the same reaction will try for 1200 degree centigrade. Now see, at 1200 degree centigrade what happened? This carbon, oxidation of carbon curve is almost same, straight line, but this iron curve change, okay, the value goes higher. If the values goes higher at 1200 degree centigrade for iron oxide, what is the value? The value is around 250. This point you see, the value is 250, okay. And for this graph, the value is almost same, it is almost straight line. So at temperature 1200 degree centigrade, iron oxide to iron and oxygen, delta G value is plus 250 kilojoule per mole, and oxidation of carbon plus oxygen at 1200 degrees almost same, and we have considered it to be minus 350. So if you sum up these two now, what you are getting? You are getting delta G value to be minus 100 kilojoule per mole, okay. So if delta G value is coming as negative, this means what? This means the reaction is possible. So if you are using the reducing agent carbon, at what temperature the reduction will be possible or the reaction will be possible? It will be possible at 1200 degree centigrade. But if you are doing the same reaction at 0 degree centigrade, you will not get the result. So this diagram will help you to get the perfect temperature and a suitable reducing agent for reduction of the metal. Thus, this diagram helps us to choose which combination is possible for reducing metal oxide and at what temperature. So both the information you will be getting from this Ellingham diagram. Okay. Now, let's see some limitation of this epigram or Ellingham diagram. So, Ellingham diagram tell us about the feasibility of the reaction, whether the reaction is possible or not. From delta G plot we can tell it, but it do not tell us about the speed of the reaction. We don't know whether the reaction will be fast or very slow. That information we don't get. We don't get about the information about the rate of the reaction. So that is one of the limitation. Next, there is one more equation for delta G, and that equation is delta G is equal to minus RT ln K. Okay, R is the universal gas constant, T is the temperature in Kelvin scale, ln is the logarithm term, and this K is your rate constant at equilibrium. It is the equilibrium rate constant. Now this formula is for equilibrium reaction. Since K is the equilibrium rate constant, this equation is for equilibrium condition of the reaction, but in the diagram, in Ellingham diagram, equilibrium state of the reaction is not considered. See in the diagram, so many temperature is given and rate constant happen at a particular temperature. Okay, equilibrium state will be getting at a particular temperature, but this graph is being given for a wide range of temperature, for a wide range of delta G. So both of this do not go together. That means equilibrium concept is not being followed in the Ellingham diagram. So some anomaly is there in the diagram. Okay, it is not the perfect diagram. So one question for you: suggest a condition under which magnesium could reduce alumina. Okay, you have to tell the condition at which magnesium can reduce the alumina. Okay, now see here, magnesium, this is magnesium and alumina. Now they have asked when magnesium can reduce alumina. You know that the element present at the bottom can reduce the oxide of other element present at the top. So magnesium will be able to reduce alumina, but up to what mark? Up to this A point. Okay, why this A point? Because after it you see the curve, magnesium curve goes up and alumina curve come down. That means after this A, that means after temperature of around 1300 degrees centigrade, aluminium will reduce magnesium, because magnesium then goes above alumina. Okay, so what is the range? From 0 degree to 1300 degree, magnesium can reduce alumina, but above 1300 degrees centigrade, aluminium will start reducing the magnesium. So that is your answer. Okay, clear? So what is the condition? 0 to 1300 degrees centigrade. Within this temperature range, magnesium can reduce alumina. Okay, next topic is thermodynamic principle of metallurgy and its application. So what is the application? Application of metallurgy, thermodynamic principle in metallurgy is will study the extraction of iron from its oxide, extraction of copper from copper oxide, and extraction of zinc from zinc oxide. So this is the next topic, one by one will cover. Okay, so that is about your application. That's all for today. Thank you.